Today we'll talk about what happens when the matrix in the equation x prime equals ax has a repeated eigenvalue. We've seen what happens when there are distinct eigenvalues and when the matrix has complex eigenvalues. Basically, when the matrix is diagonalizable, there's a very nice answer for solving x prime equals ax. And there is an answer for what happens when there's a repeated eigenvalue and the matrix is not diagonalizable, but it turns out to be a bit more complicated. So let's look at an example. So suppose we want to solve x prime equals 1, negative 1, 1, 3x. By the way, a reference for this is the book Boyce and DePrima, section 7.8, so on repeated eigenvalues. So first we'll find the characteristic polynomial of the matrix A. So that's going to give you lambda squared minus the trace. So it's 1 plus 3 is 4 lambda, and then minus the determinant. Plus the determinant. So you get 3 minus negative 1, that's 4. So you set that equal to 0. Then you factor this, so lambda minus 2 in parentheses squared, and then you see that there's only one eigenvalue, which is 2. And this has a multiplicity of 2. But we know that the only diagonalizable matrix that's 2 by 2 and has only one eigenvalue is the diagonal matrix with lambda on the diagonal. Now this matrix A is not a diagonal matrix with 2 on the diagonal. So we know that this matrix is not diagonalizable. Okay, so this matrix A has a repeated eigenvalue. It's a 2 by 2 matrix. So if you have a 2 by 2 matrix with a repeated eigenvalue and it's not a diagonal matrix, then it's not diagonalizable. So A is not diagonalizable. Right? Let's explain why. Because in order for a matrix to be diagonalizable, there has to be a basis for Rn consisting of eigenvectors. So this matrix A is 2 by 2, so we're talking about R2. Does R2 have a basis of eigenvectors of A? Well, the only eigenvalue is 2. So if there was a basis for R2 consisting of eigenvectors, okay, let's say it was V1, V2, so these two are independent vectors. If those are eigenvectors for A, then A would have to multiply, A times V1 would be 2V1, A times V2 would be 2V2, and then A would multiply, A multiplied by any vector in R2 would be 2 times that vector. And the only matrix that does that is the diagonal matrix with diagonal entries 2 and 2. So that's why A is not diagonalizable. So there is no basis for R2 consisting of eigenvectors of A. That means, but we still want 2 independent solutions, right? And so normally those 2 independent solutions are going to come from eigenvectors, but we will not have 2 eigenvectors that are independent. The most you can have is 1 independent eigenvector. So it turns out that what you can do in this case is you can try, well, you would do the same thing to find one of the solutions. So the first solution will come from V1 e to the RT. So R is your eigenvalue, okay, R in this case, or lambda. And the next one, x2, turns out to be V1, so it's the same V1, as in the x1, v1 t e to the rt plus v2 e to the rt. So that's what you do when you have only one eigenvalue r that's repeated. It turns out that this will work. It's not very obvious. You might think that it's x2 is v2 t e to the rt from your understanding of what happens in a second order equation where the characteristic polynomial has a repeated root. But it turns out that doesn't work if you try testing it. It turns out that this is what will work. And so let's see what v1 and v2 will end up being. So in this case, r is 2, right? So, well, we want to make x prime equal to ax. So in this case, x1 will be v1 e to the 2t. So its derivative is going to be, let's do x1 prime, is going to be 2v1 e to the 2t, okay? And ax is going to be, well, it's going to be this matrix 1, -1, 1, 3. Actually, it might be better not to even write that out. Just write as a times v1 e to the 2t. So we want these to be equal, right? So the first equation we get is a v1 e to the 2t equals 2v1 e to the 2t. Okay, then we have x2, so that's equal to v1 t e to the 2t plus v2 e to the 2t. So we take the derivatives, that's x2 prime, and that's going to be 2 v1 t e to the 2t plus 2 v2 e to the 2t. And ax2 is going to be, we use the linearity, a v1 t e to the 2t plus a v2 e to the 2t. So these two are the same, right? Because we want the differential equation to be true. And now if you match up the terms, hold on, let me make sure I wrote this correctly. Oh, sorry, I did not do this correctly, because you're supposed to use the product rule, aren't you, for the first one? So it's 2v1 t e to the rt plus times the derivative second plus second times the derivative first. So I have a v1 e to the 2t, don't I? Plus 2v2 e to the 2t. Okay, so that x2, okay, so then I set, when I look at my x2, and I set x2 prime equal to ax2, okay, I look at what's in front of the t e to the 2t's, and the coefficient of the e to the 2t's, and when I match those together, this is going to tell me that a v1 equals 2v1 and a v2 equals v1 plus 2v2. Do you see how we get that? Because when you look at this thing, right, I factor out the e to the 2t, I get v1 plus 2v2. So that's what's being multiplied by the e to the 2t in x2 prime. And then when you look at ax2, this e to the 2t is being multiplied by av2. So I get this second equation, av2 equals v1 plus 2v2. And then this first one I got by looking at what's being multiplied by t e to the 2t. It's AV1 and 2V1. So those are equal. So I get this. So if I can solve this system of equations, okay, I'm given A. If I can find V1 and V2 that make this system of equations true, this system, then my differential equation will be satisfied with this x1 and this x2. Do we see what's going on? So we're going to solve for v1 and v2 using this equation here, and then that v1 and v2 will give us the x1 and x2, which is what we want, because we want the two independent solutions. So now we have to solve this one, and it helps to write, well, the first one is something we're familiar with, right? v1 is just an eigenvector with eigenvalue 2. So we can write this system of equations as in terms of a minus 2i. A minus 2i times v1 is the 0 vector. And the second equation, we can subtract 2i, or we can subtract 2v2, and then take out the v2 and get a minus 2i v2 equals v1. Right, so this is the same as this. And now everything is phrased in terms of a minus 2i. So first we find v1. Okay, so first we solve this equation. v1's in the null space of a minus 2i. And then once you find v1, you can solve the second equation. Now what's kind of tricky, potentially, is that a minus 2i is not invertible, right? So since it's not invertible, there are going to be some v1s for which there is no v2. And that's something that might potentially happen. But I think in the example, at least in this example, you will be able to, just any v1 will get you a v2. So that's because this is a fairly simple example. But I'm just saying in general, you might get something, you might pick v1 and then turns out there's no v2. But if you pick the right v1, then you will be able to find v2. So anyway, in this example, I don't think something like that would happen. So a minus 2i is going to be negative 1, negative 1, 1, 1. And we can find an eigenvector easily, negative 1, 1. Okay. So that will be an eigenvector. And now we need to solve a minus 2i, that's negative 1, negative 1, 1, 1, times v2 equals negative 1, 1. We need to solve for v2. Well, from this equation, we see that v2 could be 1, 0. Right? This is going to work. So now we have our v1 and v2. That's going to give us our x1 and x2. So two linearly, turns out these will be linearly independent. Okay. This v1 e to the rt, and x2 will be v1t e to the rt plus v2 e to the rt. So the general solution is x of t equals c1 x1 plus c2 x2, right? So it's, I should have maybe been more consistent with my notation. So x1 superscript x2. So c1 x1 plus c2 x2. Where c1 and c2 range over all possible real numbers. So that's my general solution. So when you have a repeated eigenvalue, you have to use this x1 and x2, and you solve for the v1 and v2 that will work, and then you do that by just calculating x prime and ax and setting them equal, okay? And then that's going to give you this system of equations. You're going to get two equations, and then you have to solve. So it helps to get everything in terms of a minus ri, okay? And then you solve for v1 first, and then you can solve for v2, and then that will give you your x1 and x2. So it's not very clear from this, why this x1 and x2 work. You just sort of have to see that it does work when you do the calculations, but where does it come from? It's not very obvious. Okay, but when we talk about the matrix exponential and how repeated eigenvalues work in the general solution with the matrix exponential, we'll see where this comes from. Okay, so repeated eigenvalues are more complicated than distinct eigenvalues and complex eigenvalues, but this is how you would do it, at least for a 2 by 2 case.